Thank you for joining us. We're very excited for Vincent Pribble's presentation from Micro Meat. I'll pass it off to Vincent. Thank you very much.
Great, thanks, Alex. Well, hey, everyone. It's great to be here talking at CMS Astro 2022. My name is Vincent Pribble. I am the co-founder and CTO at Micro Meat. I was invited to speak a few weeks ago, and I've been working on finding something out of this world to talk about. At Micro Meat, we develop technology for scaling cultivated meat. And while we focus mainly on Earth, our technology can easily meet the needs of space applications. So before diving into how we are helping to solve those space-based challenges for growing food, I figured I'd give a quick background on myself. So prior to founding Micro Meat, I worked in the space industry, building and launching rockets for companies such as NASA, ULA, Blue Origin. I've worked on nearly every stage of launch system development, from napkin sketches for new launch systems to putting the fastest man-made object, which is Parker's Solar Probe, into orbit around the sun. I received my bachelor's from University of Illinois and my master's in space systems from Florida Institute of Technology. During my time in the industry and in my education, I've had the opportunity to be exposed to some amazing missions. And around the time I joined NASA, not only was COVID at its peak, but I also really started seeing the effects of climate change had become a lot more pronounced. I realized at that time that I wanted to refocus my talents away from simply getting to space and instead find ways to take what I learned about getting there to help eliminate the effects of climate change, as well as to improve quality of life for inhabitants on this planet that we call home. I quit my job last year at NASA in September, and in November, I began working with Dr. Anne-Sophie Merkin over at Micro Meat. So to help frame the discussion of why cultivated meat is so important to the space ecosystem, I figured I'd start by sharing some thoughts from my thesis research. At the time, I was researching requirements and architectures for how to maintain healthy human physiology on long duration space missions to the moon. And two of the key issues that I came across were the psychological effects of spaceflight, as well as caloric load requirements. Both of these make up, to me, why cultivated meat is not only beneficial, but essentially required for space. So going to space is rough, but going to space and then also having to give up on your traditions and cultures can make living there a whole lot worse. Finding ways to maintain our traditions is necessary for humans to successfully obtain the potential of space. For me, it really doesn't make sense to give up parts of who we are just to make it there. Humans are social creatures, and being cramped in a 5-meter wide cylinder for months on end is not an experience that people, especially everyday people, which are like non-astronauts, are really prepared to experience. In long duration mission simulators, which you can see on the left, astronauts have not really fared well to adapting and living in smaller areas. There's a few examples of this that exist, but there's a great one from 2014, where during a 520-day study, 6 people were sent on a 520-day mission inside of a 550 cubic meter ship and experienced a plethora of issues along the way, such as depression, insomnia, fights between the crew. And until we have long duration missions out to Mars, it really isn't possible to know exactly how badly the human psyche is going to handle this transition. So now imagine you take the same situation and now you don't allow these trained individuals to have the food that they want. Giving astronauts as close to the same experience as they have today may prove essential to maintaining their psyche. But besides psychological effects, maintaining enough calories is obviously the crux of the matter. Astronauts have the same dietary needs in space as on Earth, and as mission durations get longer, the weight to calorie ratio of what they are eating begins to matter more and more. This is obviously a challenge with a strictly plant-based diet, as not only do plants take more space for the same caloric content as meat, but they also take more time to grow to achieve the same results. At some point in the near future, the mission duration will be so long that flying the entirety of the crew's diet at launch becomes impossible. And this is where cultivated meat steps in. So using food to maintain calories and even your psyche is important, but why is it so difficult to grow right now? Well, there's three essential problems. There's a few challenges that come with growing cultivated meat. This largely stems from the fact that getting to space is still quite challenging. Using current launch vehicles in operation, Delta IV, Falcon 9, and Antares, for example, we're faced with issues that all revolve around mass, volume, and reliability. So mass is one of, if not the largest contributor to space mission architectures, mainly due to the rocket equation. If you want to go faster, you need propellant, and the amount of propellant you need is dependent on your launch mass. This increases cost as well as structural requirements, which therefore affects your mass, and you can see how this snowballs. For long duration missions where sending the crew with the entire stock of food pre-grown is not possible, farming plants and growing cultivated meat has to enter the equation. To reduce mass costs, a balance has to be made between ensuring rapid cycle time between growing the food, consuming it, reprocessing the waste, as well as system complexity and reliability. So for example, a single plant might take anywhere from 60 to 90 days to reach maturity. This is the case for common vegetables like carrots, peppers, spinach, peas, beans, all of those. For cultivated meat, from initial stem cell expansion to your final product, the growth time can range anywhere from 30 to 40 days. But this depends largely on the mass that you're growing. With efficient waste reprocessing, this could increase your food stores fairly significantly. However, this requires the right infrastructure to reprocess the waste into useful materials like growth factors. This again adds to system complexity, which increases mass. On the other hand, bioreactors require more amounts of power, more water, and cleaning than plant-based systems. This is for mixing the fluids, maintaining trace gas concentrations, as well as maintaining the fluid temperature. They require infrastructure for reprocessing the medium to eliminate cell wastes and replenish those growth factors. And after all, you must limit waste as much as possible when you're going to space. So all of these elements and many other directly increase the overall mass requirements of a cultivated meat solution. So besides mass, volume of your fairing is a huge factor as well. Today's launch vehicles have fairing sizes which greatly limit the size of systems that are available for cultivated meat and plant-based farms. These are vehicles in use today like Atlas V, Delta IV, Falcon 9. All of these have fairings that are underneath 5 meters. The good news is that in the future, in the near-term future, we have vehicles like SLS, New Glenn, Starship. They all have proposed fairings of 7-meter diameters, which definitely decreases many of the challenges associated with optimizing systems for volume alongside farming capacity. And I bring this up because in addition to being mass critical, food systems should try to optimize the useful volume of the space that is available. Using the volume available to maximize calorie output is what will make food systems for deep space missions complicated for the foreseeable future. While plants can be grown easier, they have issues with high calorie outputs while still requiring a large volume. And of course, a better architecture for all these problems is one that combines plants and cultivated meat to take advantage of both. And then, of course, we got to talk about reliability. It's another factor that at the moment is overwhelmingly important, and in the near term, it probably won't be. Current missions that nation states are launching to other planets or as flagship missions require extraordinary levels of reliability. After all, why would you launch a mission to Mars if you're not 100% confident that the rover or orbiter is going to be successful when there is no ability to recover or repair? So when thinking of long duration missions to the outer solar system, these problems only magnify. When thinking of commercial missions to LEO and the moon, however, there is enough padding there that failures can happen without loss of life. The challenge with cultivated meat versus plants is primarily here. With plants, the reliability aspect for the most part is solved. You have a seed, plant it, water it, watch it grow, and harvest. There really isn't anything that you need to do or can do. With cultivated meat, though, you have to accurately control the acidity, the sugars, dissolved carbon dioxide, oxygen, and those are just a few of the parameters involved. Additionally, this entire process must be done at a specific temperature range and in a completely sterile environment. Now, these are significant challenges when comparing plants and meat. However, those challenges have a lot of benefits when you overcome them. Now, I do need to add one caveat to all of these three factors. Most of these issues go away with a launch system like Starship. A lot of the reasons I've talked about that has made growing food in space uneconomical to date is because, first off, it costs a lot of money to get to space, and two, the crewed missions we have went on so far have not required this. For example, the cost per kilogram to orbit for the space shuttle was right around $27,000 per kilogram. So launching dirt, seeds, water, containers, bulbs, everything required to grow a single plant has been very expensive. SpaceX developing their Starship system is a massive leap in space capabilities. With previously mentioned figures being passed around like $5 per kilogram to orbit with a fully functional Starship, and with fairing sizes as large as the internal volume of the ISS, many of the current issues that I just talked about become much less problematic. So in summary, cultivated meat does have its challenges when applied to space, which is why designing space system architectures to work around these problems is required. To explain how what we are working on at Micro Meat solves these problems, let's first take a look into the overall cultivated meat process. So first off, cultivated meat can essentially be broken down into two steps. First, you need to make a lot of cells. This starts with any animal. You perform a biopsy to gather some cells. These cells can remain as mesenchymal. They can be immortalized. But regardless of this, the process to take the small amount of cells and turn it into a giant amount for consumption is done using bioreactors, medium, and growth factors. For the most part, these components are all common in the traditional biopharma industry. Bioreactors currently in use might not be the most efficient for this, but they work decently well for cultivated meat up until now. While there are still things to improve on here, for the most part, we understand how this process works, and at the moment, it's just about scaling step one. However, for the second step, this is where you need to take the mass of stem cells that you've just grown and actually differentiate them into real muscle tissues. At the end of the last step, you don't actually have muscle tissue yet. You just have tons of stem cells. and nothing has actually formed muscle tissue. The reason you don't just stop at the end of step one is that differentiating and maturing the stem cells into actual muscle tissue greatly increases the nutritional value and the texture of the meat. To do this, though, you need a thing called scaffolds. Scaffolds are essentially the supporting structure that stem cells use to become actual, fully formed muscle tissue. You can think of this just like a house. Uses like a scaffold to be built. The scaffolds aren't part of the house, but they are key to making it what it is. So cells use the scaffold to grow, lengthen, form new structures, and all of these are key to forming functional muscle tissue. So taking under consideration the main challenges I've discussed with cultivated meat in space, which is psychology, nutrition, mass, volume, reliability, we have developed at Micro Meat the ideal solution for scaffolding on Earth and in space. From Dr. and Sophie's research, we have designed a method capable of producing any quantity of scaffolding at minimum power, mass, and volume requirements while remaining highly reliable. Our machine that can produce about a single metric ton of meat, what we call pre-tissues in a day, only requires a volume of around 2 cubic feet, which is at an overall system weight of right around 10 kilograms. You can imagine the whole system like a desktop printer in size and weight. Scaffold material and cells go in, inoculated scaffolds come out. The best part is that this system can essentially make any meat at any size, even whole cut. So you might be asking too then, well, why is it difficult to make thick cuts of meat? And what's important to remember here is when you think about muscles growing inside of your own body, it's important to remember that all of those muscles are only the width of a human hair away from a nutrient supplying capillary. This is a huge issue for making cultivated meat, regardless if you are on space or in Earth. Mainly because as tissues begin to get thicker, they still need nutrients throughout. And at some point, they become so thick that normal nutrient diffusion processes stop working. In mammals, we solve this by growing large networks of blood vessels to overcome this problem, but we can't do that in cultivated meat because it's expensive to grow these large networks. It takes a very long time. And to be honest, we still don't really understand how to do this. The bottom line, though, is that if muscle tissue doesn't get enough nutrients, the cells begin to die, which signals to other cells that they should also begin to die. And then you have a cascade, and soon you don't have anything. This has been a huge challenge for the cultivated meat industry because people don't just eat thin pieces of meat. Without going into too much detail, we eliminate the need for complex vascularization by creating constructs inside of our scaffold, which allows nutrients to reach all throughout the tissue. Now, going back to psychology for a moment, obtaining a large variety of meat while keeping system complexity and mass low is required. Our technology is universally applicable, and it can be used for any species of mammal, bird, fish. It can create muscle, and it can create fat. This means that as astronauts, you could create whole cuts of beef, pork, chicken, any animal you can think of with a single solution. Add on a grinder, and now you have meat for any recipe that you can imagine for any mission that you're going on. So the other part of this is that minimizing waste of high value materials is really challenging for cultivated meat. Right now, the industry is putting a large quantity of expensive growth factors into bioreactors alongside basal nutrients. However, these proteins aren't actually used with 100% efficiency. And once the acidity of the liquid in the reactor reaches a certain threshold, the entire volume of these growth factors is removed. This means that there are still viable proteins inside the reactor, which the cells could use in the future, but they are disposed of. So systems for medium filtering and replenishment are being developed by many manufacturers to solve this problem, but we take a slightly different approach. Our method enables retention of growth factors within the scaffold itself. This increases the ability of cells to access their growth factors while reducing waste. So rather than use a ton of growth factors in the hopes that the cells find what they need, we provide everything they want directly in the vicinity of the cell itself. This reduces the need for a separate solution to filter and replenish growth factors within the medium, which reduces your mass, complexity, and then cost. And keeping in line with thinking about high reliability, none of the components required to make the machines that make these scaffolds need to be precision machined. The internal systems use simple fluid components, which in many cases can be 3D printed in space. This ensures that even in a failure, the crew can fix the error. Because the system requirements are very lenient, non-custom, and because the system only requires a small footprint to create and inoculate the scaffold, it can also be scaled to nearly any desired amount of meat production. And this not only then enables a single system for a small crew, but it also enables a single system that can grow with the crew as well, which further simplifies things like low Earth orbit, cislunar, and Martian colonization. But in summary, while our technology is finally entering production, there are many things that still need to be solved looking forward within the space ecosystem. Long-term cell storage, power efficient reactors, medium filtering, treatment are just a few of the needed pieces to solve how to grow meat in space. But in summary, cultivated meat is not only going to change how we interact with the animals on our planet, how we get our nutrients, but it's going to fundamentally ensure that our traditions and culture comes with us to the stars. While there are many issues remaining to bring cultivated meat to the masses, Micro Meat has made significant strides in solving how to make cultivated meat scaffolds scalable for mass consumption. And as for the future, focusing efforts on eliminating the complexities of this process will end up increasing the viability of the overall ecosystem. It took years of lab research and hard work by many scientists to get us where we are today. Now we need to make this process robust enough to bring with us to the stars. And of course, if you're interested in learning more about what we do at Micro Meat, feel free to reach me at the emails here. But otherwise, are there any questions?
Well, thank you very much, Vincent. I think that was a really nice, really kind of step-by-step overview of not only kind of thinking about cultured meat in space or cultivated meat in space, but also how Micro Meat kind of helps with that. I have kind of like a laundry list of questions that I'll go through here. But first, I kind of want to ask you about your background within the space industry. I know you might not have been working on food technology for space specifically, but what kind of discussions were there around food in space when you were kind of working on projects within the space industry?
I think in general, it wasn't talked about often. When it was talked about, it was mainly surrounding missions for Cygnus, for resupply to the space station. But a lot of it, I just remember a lot of missions about, or a lot of conversations about making sure that the system was balanced for launch.
Interesting. Yeah. I mean, and you gave a metric. I think it was like $27,000 cost per kilogram. And did I get that right? That with Starship, theoretically, we could bring it down to, you say 5, not 5,000?
That's, if I'm correct and I remember correctly, that is what is being talked about for the fully functional. I think they're talking about that when you get to 3 Starship launches per day, you can hit right about $5 per kilogram to orbit.
Wow. Okay. And kind of going back to, the idea of producing more or producing cultivated meat in space. I guess if we're thinking about the long-term scope of things, the equipment, for example, bioreactors needed, this is not something that would, continuously be going back, up and down. It'd be something that would go to space and then just kind of stay there and be this kind of, meat production facilities, so to speak.
Yeah, I think a great example of that would be if you look at companies like NanoRacks, where they're talking about modifying an Atlas second stage and converting it into, I think, a habitat or something like that. But those same kind of premises, right? The nice thing with the bioreactor is that the overall structure is very similar to a rocket. So in a way, in the future, depending on the volume that we end up making, that same concept of grab a second stage, throw some insulation around it, and put a mixer in there, boom, you have a giant, clean reactor for space.
I love that idea. And I'm imagining kind of, seeing these, silos or bioreactors reused like spaceship parts as kind of, the bioreactors on the moon. That's a really cool thought. I also have a note here. You were talking about that. Ideally, we would have some sort of like, I guess hybrid is the term that's being thrown around, but like cultivated meat product mixed with plant-based ingredients, and that would be for part of like the long-term sustainability. That would be plants that are grown in space. Is that right?
Mm-hmm.
Okay, interesting. And we hear a lot about that, astronauts or anyone going to space does kind of crave these like human foods. But I think, you're the first one I've heard, really talk about on a deeper level, the psychology of it and really kind of, talk about things like, depression and other kinds of things, without not having those kind of either not necessarily just foods that you are craving, but really that kind of more human feel. So I think that's pretty interesting. At Micro Meat, I know that you guys are working on technologies that work in the space, but are you guys having any plans to either from a standpoint of either research in space or maybe surveys or anything like that for those that are going to space? Are you guys doing anything directly in that arena?
We are definitely looking into obtaining some grants to continue research of our own stuff, particularly the scaffolds up in space. At the moment, I would say we're definitely focused on getting everything running on planet Earth.
Cool. And then, another, this is more of kind of like a personal question that I think that you might know the answer to is that, in the documentaries, and I've referenced this before, but in the documentaries about space, especially the recent SpaceX ones, you see people kind of like using their phones and that kind of thing. Is internet access pretty readily available, like on ISS? Do you know anything about that?
I think it is. I mean, I haven't heard any stories about people having issues calling their families on Earth. At least I would hope not. But yeah, I mean, that's an interesting question.
Cool. Yeah. And those what is it? Scott Kelly videos are just super cool.
Oh, those are fantastic.
Cool. Yeah. Yeah. I wanted to just shout out, fellow Illini here. You said University of Illinois. So
there we go.
Yeah. Do a shout out there. The last question I have is regarding, the micro meat process and how, the process that you guys are utilizing will require less medium, and that's extremely important for space because you're minimizing medium waste. But would there still be some waste, and could that potentially be recycled back into the system?
Yeah, and I think that's key is finding minimizing what you're using in the first place is key, but then minimizing your requirements that you're going to eventually put on your medium recycler and replenishment. That is the next step then to reducing the overall complexity of that system. Like if we hand that system, 10 liters or 100 liters rather than 10,000, that's a significant advantage to make sure that we don't, throw mass at stuff that we don't need to.
Awesome. Cool. Well, thank you so much. If you're interested in getting in touch, Vincent's information is right there, and we'll be having opportunities to reach out for questions as well. Vincent, thank you very much.
Thank you. It's been a pleasure.